Hello everybody, this is Felix and today we're going to learn about pressure in liquids and its relation to depth, density, and gravitational acceleration using the wonderful tool Phet Simulator. But before we dive in, let's have a look at the formula for pressure in liquids. We have P for pressure equals to H, which is represented by depth, rho, which represents density of the liquid, and G, which represents the gravitational acceleration. Now keep in mind this formula when we perform the experiment later. Alright, for those who's not familiar with Phet Simulator, it's just a great online tool to experiment with physics concept. All you need to do is type Phet Simulators on Google and you'll be set. So inside here you have multiple different experiments to play with, and today we will be doing the one which is under pressure. So before we begin, let's start by placing our pressure gauges at different levels over here. Note that all these pressure gauges are at different heights according to this, and I'm just going to release the water and we'll see which one has the highest pressure. So now before we start, can you guess, according to this formula, P equals to H rho G, which one will have the highest pressure? Keep in mind that depth is measured from the surface of the water. Alright, let's have a look. Alright, did you guys guess what happened? So as you can see, the deeper the pressure gauge is, the higher the pressure, which is true, which actually proves this formula correct, where the bigger this number is, the bigger the pressure would be, as we measure height from depth from the surface of the water. Alright, so let me just reset this and have a look at this. What about here? Would the pressure over here, these two, would they be the same? And let's get rid of this. And the pressure for these two, would they be the same? Now we're experimenting with different container shapes. Let's see how it will be affected. Keep in mind this formula again. Right, let's fill it up. And as you can see, the shape of the container does not actually matter. Yes. What really matters is actually the depth or the height from the surface of the water. Okay, so now let's reset this and bring this all back. Let's reset this. Let's put this pressure gauge in the middle and fill it all up. Alright, so let's look at this formula. We've already played with H. Now let's try playing with the density of the liquid. What do you think will happen if we increase the density? Obviously, if here there's an increase over here, the pressure would most likely increase. Let's see whether that will show. Alright, let's slide this to increase from the density of water to honey. So you can see there's an obvious increase in density, and look at that. The pressure of the gauge also increases. And if we decrease it down to like gasoline, the pressure also decreases. Now let's bring it back to water. Now let's have a look at gravitational acceleration. Same story. As this increases, your pressure would most likely increase. Let's see whether that's true. So we have three planets here: Mars, Earth, and Jupiter. And Jupiter is the largest in mass compared to Earth and Mars is slightly smaller than Earth. Therefore, the gravitational acceleration for Jupiter is a lot higher than Earth, and then Earth's gravitational acceleration is also higher than Mars. So in theory, if we go to Mars, what would the pressure of this be? Let's have a look. It will decrease down to 45 kPa. Now, what if we were to increase it all the way up to Jupiter? Look at that. As the gravity increases, the pressure will also increase and has already exceeded its scale. So, now we have actually shown how P equals to H rho G, where P is pressure, H is the depth of the liquid, rho is the density of the liquid, and G is the gravitational acceleration. I do recommend you guys head over to Phet Simulators and find this demonstration so you can have a fun playing around with these figures and see how it actually affects the formula. That's all from me today. Hope you have a great lesson, and I'll see you in the next episode.